When we're rationalizing that denominator, we're getting that square root out of that denominator. So let's start with a simple one. We are trying to simplify that denominator. We're trying to rationalize that denominator. And so we want to complete that square root. So I need to multiply by the square root of 5 divided by the square root of 5. Because we need to get rid of that square root in the denominator. We're basically multiplying by a 1 in disguise. Just like whenever you had to add fractions, you had to get a common denominator. Same idea. We're multiplying by that 1 to create that denominator of choice. I am going to show you some of you are going to be able to find shortcuts to not have to show every single one of these steps. There are a lot of shortcuts involved. I am going to show you every step. So that's going to create the square root of 25 in the denominator. What's 1 times the square root of 5? Okay. So what is the square root of 25?
5.
And that square root of 5 stays in the numerator. I'm done. These are going to sometimes look more complicated than what we started with. So, even though this is called simplifying, doesn't mean it looks prettier. Just be prepared for that. So let's look at this next one. We have 2 times the square root of 8 divided by 5 times the square root of 10. So we want to get rid of that square root in that denominator. So what 1 am I going to be multiplying by? Square root of 10 over square root of 10. So that's that 1. In the numerator, that gives us 2. What's under our square roots can multiply together. That 10 and that 8 will multiply together to give us what? 10 and 10 multiply to give us 100. So we have 2 times the square root of 80 divided by the square root of 100.
Where'd the 5 go?
Oops, I forgot the 5. The 5 is there. So what is the square root of 100?
10.
You can use the upside down division to find that if you don't see it otherwise. That denominator should have no square roots in it at the end of this. Otherwise you did it incorrectly. And so let's take our numerator. The 80 is still under a square root. So let's see if there's any perfect squares that can come out of 80. So dividing it by 2 gives us 40. Divided by 2 gives us 20. Divided by 2 gives us 10. Divided by 2 gives us 5. So I have a set of 2's and another set of 2's. So I have, what is 2 times 2?
4.
So I have that 2 that was originally there times the 4 I was able to bring out. And I'm leaving behind that square root of 5 that got left over. So this is what was that square root of 80, just written a different way. What is 2 times 4?
8.
So I have 8 on the square root of 5 divided by 50. Now, can I reduce under the square root with anything?
No. You can divide by 2. 8.
We cannot take what's under the square root and change except to bring out perfect squares. So what's under the square root is going to stay the same unless I'm multiplying by something or bringing out perfect squares. So I cannot reduce it with the 5 and the 50. But I can, the 8 and the 50, what's outside the square root. 8 and 50 are both divisible by?
2.
Giving me a 4 and 25. So my final answer is 4 times the square root of 5 divided by 25. That's the answer. And like I said, some of this math, especially those that like to do a lot of mental math, you may be finding shortcuts as we're going through this. That's fine. Just be careful in taking too big of steps.
Can you go back for like 0.2 seconds?
What's different with this problem?
There's the negative sign.
The numerator is separated by a
Negative.
subtraction sign. So it's a binomial in my numerator. So that means that I need to take, and there's going to be 3 places I'll be looking at when I'm canceling. And 3 places I'm going to be looking at when I'm multiplying. So what is my 1 in disguise I'm going to multiply by this time? What do I need to get? That's square root of 21 divided by square root of 21. What's going to be different, because that binomial's in that numerator, I have to distribute that square root of 21 to both pieces. Because it's separated by that negative, that subtraction sign. Because that's there, it's going to cause me to distribute. So in the denominator, I have the square root of 21 times the square root of 21, which is not 42. That's,
You said add it.
No.
I said times.
441.
440, 41. Okay, in the numerator, when I distribute, 4 times the square root of 21 minus, what's 6 times 21?
126.
So let's see what we can simplify. We're going to take each of these places under square roots and see if there's any of them that can simplify. Always in your denominator, check and see if you can take the square root of it. Can you take the square root of 441?
Yes.
And that gives us
21.
Now let's take the other spots. 21
No.
gives us a 3 and a 7. Do I have a set of anything that can come out of that? Nope. Let's take the 126. Divisible by 2 gives us 63. 63. Divisible by 3 gives us 21. Divisible by 3 gives us 7. Do I have a set? A set of 3s. So that 4 times the square root of 21 I couldn't change. Minus the 126 I could. I could bring out a set of 3s and leave behind the 2 and the 7. What's 2 times 7?
14.
That's what got left behind. Now, take my coefficients in front of my square roots and my denominator. Is there any number that divides into all 3 places? No. My answer.
How did you make the negative, or the 2 negative, the 7 negative?
Why did I make the 2 negative? Where's it?
Oh.
That was, sorry, no, that was just me pointing. Sorry.
Oh.
That was me highlighting what was left behind, not negative signs. Sorry, I should use another symbol. That better? Okay. We don't always have square roots. Think back to last week, we worked with higher power roots. To complete a higher power, we need a set of whatever our index is. So let's look at our denominator. 25 is made up by 5 and 5. What do I need to complete 4? I need 4 of them to be able to complete it. So what do I need extra? So I have 2. What do I need to complete that?
Add another 25 to
We need 2 more, right? So my 4th root of 25 would complete it. Because I need 4 of those 5s. So in the numerator, I distribute 3 on the 4th root of 25 minus the 4th root of 625 divided by the 4th root of 625. 25 times 25 is 625. So I just multiplied these two numbers. That's what got this number here. In the numerator, I took 3 times what I was distributing to it minus these two being multiplied. So 625 was, when I factored it, what created what I've circled in green. Does everybody agree? Or do you want me to show you that?
yeah.
5 gives you 125. 5 gives you 25. 5, 5. So you have that set of 5s. Set of 4 because our index is 4.
What does that have to do with anything? Like, why can't you just multiply? Like, isn't that all you did? Multiply the 25s?
Yeah. But we need to simplify the square. We need to simplify what's in our radicals. And so to simplify it, we need to find out what perfect sets can come out. And this time we're looking for perfect sets of 4 of the same number being multiplied. And so in this case, that would be a 5 in the denominator. 3 on times the 4th root of 25 minus 625 we said is going to create 5. That's your answer. So this time we had the 3rd root of 6 minus 2 divided by, oh, that's supposed to be a plus 2. The 3rd root of 4. So what is 4 made up of? What are the factors of 4? 2 and I need to complete it. What do I need to complete it? We need another 2 because we have a 3rd power. So we need 3 2s, so I need a 3rd 2 to complete it. So in my numerator, I am going to distribute it to both parts because there is a separation of an operation of either addition or subtraction. So the third root of, what is 6 times 2? 12 plus 2 times the third root of 2. I multiply that positive 2 times the third root of 2. In my denominator, I have the third root of 8. Let's take underneath each of those radicals. So under the first radical we have is 12. That's divisible by 2, 2, and 3. Do I have a set of 3 of any of those numbers? I only have 2 2s and 1 3. So no, I don't have a set of anything for those. So that's going to be written down just like it is. Does everybody agree there's nothing to bring out of the third root of 2? It's prime. So just write it down. My denominator, 8. So I have a set of 3 2s. So 2 gets written down. Is there a coefficient in front of every single one? There's not one in front of the cube root of 12. It's understood to be 1. You're right. There is a coefficient of 1. But is there anything that can divide into all 3 of those places? No. So this is our answer. Now for the easy part. So imaginary numbers, I is the square root. I is the square root of -1. So we can't leave an I in the denominator either. But what's nice is if you have a monomial, meaning nothing being separated by addition or subtraction in the denominator, that means I get to multiply by my 1 in disguise is going to be I over I. Every single time. If there's not an addition or subtraction in the denominator, it's going to be I over I. Any questions on that one? Is that going to change? Not as long as there is no addition or subtraction in the denominator. So my numerator is 9i. My denominator is 8i squared. What is I squared? So that changes to a -1. So I have 9i divided by -8. We do not leave negative signs in denominators. What happens is that negative sign just moves to the front. Then you have your answer. Let's step it up a notch, and we're going to do one more. Our numerator is 5 plus 4i. Our denominator is -9i. What is my understood imaginary number in this case? Or what is my understood number 1? I over I, right? You don't have to multiply by that entire denominator. If you do, it's just going to create more canceling that you have to reduce. It's not going to be an unrecoverable thing if you accidentally do it. So we distribute because there's a binomial in my numerator. So it's something being separated by addition or subtraction. We need to change out our I squareds to become -1s. So we end up with 5i plus a negative 4 divided by a positive 9. Plus a negative 4. Is there a better way of writing that? Done. That's your answer.